So, hello, it's lecture 3. So today we are actually going to start with machine learning. So if you haven't heard about machine learning and don't know how decision trees work or linear models, so maybe it's going to be exciting for you, like uncovering some mysteries. So actually the first 2 weeks were about preliminary data analysis. In machine learning, it's typically done only for actually getting insights from your data, which helps you better understand these and create some features. So the final goal, of course, is actual machine learning. And today we cover supervised learning. So it's a setting where we've got data and labels. So typically we'll have some data set. We'll call it X. It consists of metrics with instances and their features. So these rows will correspond to our observations, instances, let's say clients. And columns will correspond to features. And we are going to predict some target feature Y with that. So Y is typically the same feature as those, but we are interested in predicting it, so we'll call it a target one. A target vector or a target feature. And altogether, these will form a training set. So for now, let's pay more attention to working with it, to building algorithms, to understand data. So this vector Y is not really very easy to get sometimes. So from one viewpoint, it's from business side, it's not really obvious in each case what is actually this vector Y. We'll have a ongoing example with churn, so or with let's take a simpler one with credit scoring. So this vector Y might be zeros and ones. Zeros and ones for good and bad clients. And actually in banks everybody calls them good and bad depending on the task. So if it's just zeros and ones, we'll call this binary classification. So for now, we'll stick to just to binary classification. But it's a common case, it's a particular case of a broader family. So in supervised learning, we typically distinguish classification, like this one, when we predict some label, and we've got only some limited amount of labels. In this case, only 2. Either a client is good or bad, or it might be also a multi-class classification. Let's say predicting whether this drawn picture depicts handwritten 0 or handwritten 2 or handwritten 8 or 9. So that in this case, there will be 10 classes like that. So it's all about classification. If the target vector is actually a numeric vector, then it will be called regression. So at this point, it differs a bit with statistical view. In statistics, regression is typically what we'll call ordinary least squares or generalized linear models. In machine learning, typically by regression, we just call the task of predicting a numeric vector. So if values of Y can be anything numeric, then we'll call this regression. And there are much more supervised tasks, but these are the most important ones. I would say the third one is ranking. It's about search system, and in some sense, it's a mixture of classification and regression. So in ranking, we can predict any score. So the target can be anything, like in regression. But still, we would classify, it also resembles classification in a sort of, we typically need to predict an event, whether a page is interesting, whether a document is relevant, and the same for recommendations. So recommender system is a particular case of ranking. We'll go to ranking in the end when we'll discuss gradient boosting, which is able to do all 3 tasks: classification, regression, and ranking. But for now, we'll just stick to classification for this topic and next 2 ones. Then we'll cover regression and finally return back to classification. And another family, a really big family of algorithms, will be unsupervised learning. For now, I will only tell that supervised learning can be challenging in terms of exactly this target vector y. It can be really very expensive to get it. So from business perspective, it's not always really clear how to define it. So let's say churn. So whether a client is loyal or a client has churned, how we actually define it. In telecom companies like KPN, it's typically some definition like whether a client dropped using telephone for half a year and has sent less than, let's say, 4 SMS, then we treat this guy as churned. But it totally depends on your business task, what is relevant for you, how you actually define churn. In business tasks, it's also very important to have the same definitions for all sides, for managers, for data scientists, for third parties, if you've got, for consultants, if you've got consultants in your task. Okay, so actually in this course, we skip all of these. I would only mention that it is really sometimes financially challenging to have a nice data set. Let's say for neural nets, we need sometimes the 5th order of magnitudes, or for instances, let's say 100,000 or almost millions of labeled images. So labeled instances, whatever it means. Okay, so a common example is image classification. It's not the simplest one because we don't touch image classification in this course, but it's a really nice example to grasp how difficult it can be to gain this labeled set. So you'll need, let's say, 200,000 images to do classification into cats, dogs, penguins, whatever. And actually, to train a good model, you'll need really many examples, many photos labeled as cats, dogs, or even something more complicated, like put in rectangles showing where actually these objects are located. Okay, for such tasks as credit scoring, we also need a big data set, and at some point it can be challenging. And there will be lots of statistical assumptions, like if the training set size approaches infinity, then something is valid. And this is the main reason why more data is always better. So with more data, you train better models. Okay, there is also a joke that more data, more problems. So if you really have petabytes, you need to invest into your infrastructure. Maybe you need to switch to Hadoop cluster at some point. Okay, but let's think that our task is defined. So I'm not going to define it mathematically strictly for now. Let's just understand that we've got rows, instances with features, and we're going to predict a target, which for now will be just zeros and ones. And so for our running example, these features might be age, salary, and so on. Let's say we'll have bank clients, and we're going to predict default on their loan. Okay, so today we'll be covering decision trees. It's actually one of the most ancient algorithms. I think maybe linear regression is only older than decision trees, but they are really very popular. Not by itself, because it turned out that they are really very, very nice algorithm as basis for random forests and gradient boosting. But these are also very important because they are really very well interpretable. So there is some connection with how we actually reason. So here I show an instruction. It's taken from my university. If you've got a publication, you need to somehow categorize it. You need to upload it onto a university website, and you'd better pick one of these categories, whether it's a book or article or part of the book. And actually, this is an instruction. It shows you that if you've got an article, it's from mass media, blah, 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 then just write a letter. If you've got a brochure, you'd need to pick a label book, and so on. So we can really easily grasp this instruction. And if we take a look, mathematically, it's a tree. Okay, so I'm not going to define it strictly, but we've got a root. So here, this header is a root of the tree, which format to choose for your publication. Then we have some intermediate nodes, like this one, mass media or scientific journal. And then we'll have another nodes. They're not really different from these intermediate nodes, only that they don't have children. So some nodes below them. So that's why we'll call these leaves. So really nice analogy, a tree, and it has leaves. So a bit further, we'll call this a classification tree. So we have some such conditions, some features, and we'll have some leaves. Okay, closer to our example with credit scoring. So suppose we are a bank, and we need to somehow approve or decline clients with their loans. And how this process was built some 60 or 70 years ago, we would take some experts, some guys really proficient in finance, in these credit loans, and we'll have our client interviewed by these guys, by these experts, and experts would ask questions like, what's your age, how many children you've got, what's your salary, if it's not confidential. Okay, bank obviously shall know your salary to give you a loan. Okay, and lots of questions like that, and then finally this jury, these experts decide whether to give somebody a loan or not. Okay, and suppose these guys collect some experience, and then they need to explain how they actually work to some new employee, to their new colleague. They can actually generate such an instruction, almost the same as this one, only that now it's a bit more formal, it resembles more a tree now, and then they can explain something like that. You see, when we've got a client older than 40 years, we go here, so condition yes, he's older than 40 years. Then we take a look at real estate, whether this guy has some real estate. Then we issue a loan, so we suppose that this is really a mature guy with some real estate in possession. So this guy is going to be reliable, so we actually accept this loan application. If this guy doesn't have a real estate, then we take a look at income, whether it exceeds some threshold, we issue a loan, and then we decline. Okay, so maybe it looks really simple, but that's how it worked around 50 years ago. But now, imagine that we've got much more loan applications, and we start collecting data, and we build infrastructure to actually gather such, to collect such history, whether clients are reliable or not. And we can actually keep track of all these features and the final events, whether we declined or approved loan applications. So we start collecting this training set. And suppose we are now a really huge bank like ANG or ABN AMRO, and we've got lots and lots of loan applications each day. Of course, we can't gather these experts, this jury for every client. We'll want to build these rules automatically. And here, decision trees arise. So the main idea is to just have a training set and generate such a tree automatically. It's going to be really exciting because we'll be able to build plot like this to actually depict this tree and check how it works, which conditions it tests. We can then compare it to some expert knowledge to show it to these guys, to experts, whether they find this tree reasonable, what actually a decision tree built. So it's going to be interpretable and really nice to work with it. Only that we'll have much more advanced algorithms which work better than decision trees in terms of accuracy. Okay, for those familiar with a game, I think it's called 10 questions or maybe 20 questions. So the game is really simple. You imagine some celebrity, and your partner is going to guess who it is, and your partner can ask any questions. Any binary questions like man or woman, so male, female, whether this person lives or died already, and so on. The main idea is just to pick really nice features, really nice splits. So in this case, in this 10 questions game, we'll first ask really some general questions like, is this male or female, alive or not alive. We won't ask whether this person is French or Vietnamese, so it's not too general. It doesn't eliminate lots of opportunities. So we'd like to specify our questions, and we'd like to be able to eliminate all not suiting options. And of course, we'll ask general questions like male or female, because we split almost in two halves all our audience. And pretty much the same idea with decision trees. So here we picked age as compared to 40 years, Maybe because it's really well at distinguishing good and bad clients. And we don't pick here something really specific, like whether this client has green or red clothes, shoes. Okay, so not very, very specific questions right here close to the root of the tree. Okay, with shoes and clothes, it's an artificial example, but we are not picking such a condition whether the guy is from Den Haag or Paris or London. Maybe it's too specific to be placed here. But the deeper we go into this tree, the less instances we have and the more specific questions actually arise. So let's go into this algorithm, how we built this decision tree. So here is some math. Actually, if you like information theory and philosophy, there is much place for you to actually go deeper into it. So really nice connections with Shannon's entropy and information theory. But here I'll explain it just in terms of arithmetic and only logarithms. Okay, so Shannon entropies is just a function of some system with n states. So if we've got n states, we can define some function. In our case, there will be only two states, whether a client is good or bad. But it can be generalized to any n states. Let's say whether something is, whether a picture, an image is a handwritten 0 or handwritten 1 or so, and so on, or any system of n states. Okay, so if we just define some system, I'll depict it with just little balls like this. If we have a system with 3 black balls, 2 green ones, and I would say 3 red ones, or 4 red ones, let's call this a system. So I'm not really very strict about that, but you'll get an intuition. So this is some system that we've got. And let's define these as states. So the first state will be a ball being black, then a ball being green and red. So these are 3 states. So these are actually states. And we can define a function. Actually, it doesn't have any sense. Only the difference of this function in different states will have a sense. Okay, there are really lots and lots of foundations for why it shall look like this and what it stands for. But for now, this will be an idea of a chaos in our system. So let's formally define it a bit more formally. So here we've got some probabilities of being in state I. So here Pi is actually a probability of an object or an instance being in state I. And here let's just estimate these probabilities given our actually training set or the system that I've drawn here. So suppose I'm just picking a ball at random. So I've got a probability. It's not mathematically strict probability. It's frequency estimation. So let's define P1 as a probability that I pick a black ball at random. So this, I would say, will be probability of a random ball being black. And I can estimate, so I would put a hat here. It's actually an estimation of a true probability. Okay, I can estimate it as just by frequency. There are 3 balls, and overall there are 9 balls here. So with probability 1/3, I'll just grab a black ball from here. And the same for P2. For green, it's 2/9, and for black, it's 4/9. Okay, if I've got 3 states with 3 probabilities of these states, I can already define some function. I'm not calculating it, so not really nice to do it by hand, calculating a logarithm of 2 of some expression like 2/9. Let's just underline some properties of this function. It's non-negative, and it can be anything up to infinity. So probabilities are actually lower than 1, so this logarithm is going to be negative. So the whole expression is going to be non-negative. Again, no sense at all in this expression by its own, but let's just see how it helps us building a decision tree. Just some intuition that this expression will designate a chaos in our system. What we define by chaos here, suppose I've got a second system where there are only black balls. I would say there is no chaos here in this system in a sense that if I pick a random black ball, if I pick a random ball, it's going to be black. So there's only one state, P1, with probability of 1. It's always going to be a black ball if I just pick a random one. And here entropy will be equal to 0. There is logarithm of 1. You see log 2 of 1, and it's going to be 0. And its entropy is going to be some measure of chaos. The higher entropy, the higher is chaos in our system. And here, if I've got 3 states with such probabilities, we can calculate entropy, and it's going to be some positive number, something greater than 0. And it would mean that there is some chaos in our system if I just pick a ball at random. I'm not sure whether it's black, green, or black, green, or red, sorry. I can only give some estimation, some probabilities, and we can define it in numbers as entropy. Okay, and really lots and lots of applications in physics. So there is a second law of thermodynamics where they define entropy in another sense. And there is a really general and I would say philosophical law that entropy of a closed system cannot go down. It can only increase. So if we are doing nothing, chaos can only increase. So if we don't do anything in our house, chaos can only increase, and we need to do some work. So the system is not closed anymore. We do external work to actually decrease chaos in this system, decrease entropy. Okay, so actually the foundations for that concept were done in informational theory. If you're interested in that, this Shannon entropy also designates the shortest code to transmit a message. So if we'd like to somehow encode our message, we'd like to make the code most efficient so that we use as few letters to encode an original message. And this is almost an exact formula for an optimal code. Okay, but let's dive into how it helps us to build a decision tree. So a really toy example, we'll have only one feature. It's numeric, so just feature x from 0 to 18, but it can take any value. And we've got these balls of 2 types. They are either blue or yellow. And you see there is a really nice connection with binary classification, so we'll have more features like this one, and we'll have 2 target classes. So let's say blue balls will designate bad clients, and yellow can designate good clients. So it's really very, very high level example of a binary classification task. Okay, let's split this into 2 subgroups according to a feature, according to comparing this feature to some threshold like 12. We'll go deeper into it, how do we actually choose this 12, but let's just see how we split these balls into 2 groups. Okay, so take a look to the right one. They're almost all yellow balls here. In some sense, there's much less chaos here in this right group. So if we pick a random if we pick a random ball, it's almost certainly going to be yellow. So we can estimate probabilities. So 6 over 7 that it's going to be yellow, and only 1 over 7 that it's going to be blue. And still much more chaos left in this left group. And actually what's nice about entropy, that it can characterize it in numbers. So we'll use it for optimization. Okay, so we can calculate entropy of the initial system. I will designate it here with S0. So we've got 9 yellow balls and 11 blue ones. So two states with probabilities 9 over 20 and 11 over 20. And we calculate entropy, it's something close to 1. Okay, why is it so close to 1? There are almost equal numbers of yellow and blue balls. And if we pick a random one, we are not going to know whether it's blue or yellow. Let's just go into this formula only once. For the case where we've got equal number of different classes. Okay, so let's say this is our system again, and we'll have pluses, these are good clients, and we'll have minuses, bad clients. And suppose there are equal amounts of them, so 3 and 3. If we pick a random object, it's going to be with probability 1/2, either red, either good or bad. So this P1 is going to be probability that the random instance is positive. P2 will be the probability that the random object is negative. And we've got two probabilities with 1/2. We can calculate entropy for this state. So it's going to be minus sum over all states, I from 1. But we've got only two states, either red or blue, either good or bad. Pi and logarithm of pi. And in this case, it's going to be really simple. Pi's are equal to 1, 2. So each element here is 1/2 over log 2 of 1/2. And we've got minus. And under sum, we've got two summands like this. OK, so if we calculate it, it's going to be just 1. So in case of binary classification, the maximal possible entropy is 1. And entropy is going to be either something between 0 and 1. OK, this logarithm is -1. We need to, so 2 to the power of -1 is going to be 1/2. Here we've got 1 and -1. OK, so the final expression is just 1. For binary classification is the maximal possible entropy. And here what we've got in this initial case, 9 yellow balls and 11 blue ones. So entropy is almost 1, a bit less. If we calculate entropy in these two subgroups, it's about 0.96 in the left half and only 0.6 in the right half. So we see entropy is much lower in the right subgroup, and it really correlates with our intuition that there is much less chaos here in the right subgroup. Okay, and hopefully this entropy is some metric, some criterion to actually express the same in numbers. And then we can define information gain as the average decrease in entropy. So we've got S0, our initial entropy, and we've got S1 and S2, in our case, left and right subgroup, and we've got entropies in these states as well. And we are going to decrease the averaged entropy from the initial one. Why do we need to take into account the number of objects in each subgroup? Okay, so what we actually do here, we'll take into account that we'll have 13 objects in left subgroup and only 7 in right subgroup. And what we are calculating here from initial entropy S0, we'll actually take S1 with minus, but we'll weight it with 13 over 20. It's so 13 balls, 13 instances in left group, and 20 is the initial number of balls. So we'll just account for the size of this left subgroup. So 7 balls here in the right subgroup, and we'll account for its entropy, but only with coefficient 7 over 20. Why not calculating something like S0 minus average, minus 1/2 S1 plus S2. Okay, it's also possible, but it's not interesting because here an optimal strategy. So if we define information gain like that, IG, we'll call it information gain. If we define it like that, I'll put some sign here. Then it's not interesting. An optimal strategy will be to pick initial balls, initial objects. So a split that will maximize this one is not going to be interesting. It's only dividing something like that. One moment. So why do you think it's going to be an optimal split? Because in the left group we'll have entropy of 0. Yep. So here S1 is going to be 0. Here in S2 is going to be something close to S0 initial entropy. It's not going to be interesting because this will be an optimal split. because we have 0 here, and then we are averaging. Let's just account for the size of this subgroup. So we'll put 1, 2, 3, 4, 5, 6, 7, 8. We'll put this S1 with coefficient 1/8, and this S2 with coefficient S 7/8. Now it's going to be much more interesting. So we'll calculate an information gain. Why is it called like that? So you see, entropy stands for chaos. So if we decrease entropy, it's some sort of decreasing chaos, and that's what we'll call information gain. So we now know more about our system. It's some sort of information gain. Like in the right subgroup, we now know much more about this right subgroup. So almost certainly it's going to be a yellow ball if we grab something. So we've got some information gain in this right subgroup, and we'll average it for every split. So it's a function of a split. So here our split is comparing our feature with 12. So we can define this information gain for any split. And what we'll actually do here to start building a decision tree, we'll check split like that, x comparing to 1, then with 2, with 3, and so on. And then we'll choose an optimal split according to this information gain criterion. Well, a bit smarter. We're not going to check every possible split, but these are details. So the idea is that we'll check a feature and a split, and we'll choose the best split according to information gain. And in this case, it's actually going to be x as compared to 12. So this is going to be a binary feature, which maximizes information gain if we split by this feature. We can calculate it, it's 0.16. If we calculate the same for other splits, it's going to be a bit less. And then the algorithm is recursive. So we do this simple procedure for every subgroup. So we'll be searching for the best split in left subgroup and then in the right subgroup. And if you're familiar with recursive algorithms, the idea is that you define some simple routine, a simple function to calculate, a simple action to do, and then you repeat it in subgroups. So here a simple routine is actually calculating a feature that maximizes information gain, and then we recalculate this routine, we execute it in every subgroup. So the same for left group, then for the right, and then recursively. So we'll have a decision tree like that. So let's call it for now just a tree. So we do the same in left group and so on. And a stopping criteria might be something simple like when we've got objects, instances of the same color, obviously we can stop here, no more need to split. So here we've got entropy of 0. So a really very simple criterion will be entropy equal to 0 in every subgroup. Okay, and so we built a tree like that, and it's going to predict us the color of this instance based on only one feature. But you see the idea, we'll have much more features like age and gender and salary, whether you've got real estate or not, and we'll be choosing the best split at any point among all features, and that's how decision tree will be actually built. Okay, so now we can return here, and we can understand that here age compared to 40 is a really cool binary feature that splits our data and maximizes information gain. So again, what's an ideal solution, ideal situation? So suppose we've got some magic feature. So the initial data set is like this. We do binary classification, good and bad clients. And suppose we've got an ideal feature. So we check some binary feature and binary criterion. If it's the case, then we'll leave only, let's say, good clients. When it's not valid, then we'll have only bad clients. Good and bad. Okay. What's actually this feature is? It's our target feature, right? It's y. So it's an ideal situation. If this is the case, then it means that we left our target feature in our data set. It's not interesting. But it's an ideal case, and we can make sure that we can easily see that here entropy, what we called S1, is equal to 0, S2 is also equal to 0. Initially we had some entropy, let's say here it was 1, and information gain here is 1 minus 0, 0 multiplied by something, so information gain is equal to 1. And it's the maximal possible information gain. Okay, so this is not the case. We'll not have ideal features like that. Otherwise, we don't need to do any classification. We've got a magic feature. But the idea is that here, age compared to 40 is a really nice feature that has a very high information gain. And then we split with this feature, and then we do this something similar. We find the next best feature in any group, and finally we get a decision tree like that. Okay, but actually we'll stop at some point. So we're not going to build this tree until there are only pure leaves in terms of all instances of the same class. We're not going to do that. And here we switch to a very important question of overfitting and model selection. Okay, so now it's clear how decision tree is built. We'll do it in code, and we'll visualize this tree, and we'll actually take a look at this knowledge that actually decision tree builds. Okay, so there's honestly a lot of bullshit about that a model finds some knowledge. What is knowledge? How you define it? But in some case, intuitively, we understand it. So a decision tree produces something like that. Okay, we're not going to define knowledge, but in some sense, it's some sort of a knowledge. Yep. So if these features are not so obvious, not age and real estate, but something really complicated, some features of physical particles, but we see a decision tree building some rules, and this can correlate with expert knowledge. So it's really fascinating. Okay, but we're not going to build it until the end for the reason to generalize to new data. So remember, we built it with our training set, and the main idea of all algorithms in machine learning is not to overfit. So now we go into the definition, not formal again, but we'll have a training set like this. X is the matrix, Y is a vector, and we'll need to predict the very same Y vector, but for a new matrix xt. Let's say it's a test set. So we're going to build some model. I draw a small tree here. It's what we'll build with the training set. But the idea is to generalize to new data, to be able to produce a really nice vector yt. So it's our prediction. And we want this prediction to be really good. We'll define what we mean by good, but obviously we'll maybe in some time we'll get final answers for these test questions, and we'll be able to compare it to the actual targets for this test set. Okay, this y vector, we've got it only for training set, and for test set we don't know it. But when finally we know it, let's say clients churn, and we make a prediction whether they're going to churn or not. This is our prediction. I'd better call it P for prediction. Okay, and maybe we wait some time, and then we've got a target vector yt with actually answers for the test set. Okay, and finally, at some point, we can compare this P with Y. So we'll calculate some function. For now, I will call it accuracy. How good is our model? It will be a function of our predictions, P, and vector yt. Okay, but at the point of building the algorithm, we don't know everything from here. Yep. So it's unknown. We'll know it only, maybe we'll know it in future. And we've got only our training set and target vector y. We need to somehow estimate our model with this vector y. Okay, what's the problem of building a really, really deep tree? So let's return to this picture. Remember, the deeper we go into this tree, the fewer objects, instances are there, and the more specific questions arise. So age as compared to 40, is a really nice feature. It splits good and bad clients very well. So that's why it's picked up here in the root. Real estate is also going to be a nice feature. That's why it's here. Not as good maybe as age compared to 40. But the deeper into the tree, the more specific questions like whether the city of origin is London or Paris or Rotterdam. And suppose we build a really very, very deep tree until each leaf is pure. Only bad clients or only good clients. Eventually, somewhere here in the bottom of the tree, we'll have really, really specific criterion to split. And this will overfit to the training set in a sense that it will almost remember the training set, and it's not going to generalize to new data. So to illustrate it here, it's really hard to define overfitting strictly. It's now a really complicated theory arise, but we will understand it by a really simple reason. If the reason is building a really deep tree, and this idea of checking very, very specific questions will help us. Okay, so suppose it's our training set, and here we, at some leaf really deep in our tree, we have some criterion whether city is London. Okay, and suppose in our training set we've got only 17 guys from London, and we make this split, and 10 of them are going to be good, 7 bad, and so these will be our leaves. Only good and bad here, but you see, we actually built separate rules only for guys from London. Okay, one moment. Okay, so it's London. But suppose we've got many cities like that, and we generate such binary features comparing city to all other values. And suppose somewhere here it's not London, but Liberty. Okay, some really, really very, very small town somewhere close to Moscow. You even can't pronounce this name. But okay, a really very, very small town. And suppose we've got only 2 guys from this small town. One of these guys is good client, one of them is bad. But you see, in a decision tree, we generate a special rule just for 2 guys from Liberty. And this means that we generate 2 specific rules. They are going to work really only on our training set. They're not going to work on some XT test set. Maybe we won't have any guys from Liberty, from this small town here in test set. Maybe it's only a coincidence that one of them is good and one of them is bad, but you get the idea, yep. So we're not going to build 2 specific rules, and a really simple heuristic to restrict a decision tree is just to put a limit on its depth. So we'll just cut tree here. So let's say we'll set max depth, and it's already an sklearn argument name. Let's say we put maximal depth of 3, so we're not going to build a tree deeper than 3. So we calculate, here is going to be level 1, so then we do first split, then a second one. Okay, according to my picture, it's going to be 2. Okay, so we are just restricting the tree depth. Another really interpretable and nice criterion for stopping is minimal samples in a leaf. So again, sklearn's name for that, min samples leaf. Let's say it's 5. That means that if there are 5 or more instances in our leaf or samples, here samples actually stands for an instance. Okay, some confusion maybe here. Minimal number of instances in a leaf. If it's 5 or more, then we generate sort of general rules. If it's less than 5, these are going to be too specific. And so that means that we're not going to generate rules for 4 or less instances in our dataset. 5 is a minimum. Okay, so in this situation, we had only 2 guys from this crazy town, Liberty. Okay, 2 is less than 5, and we didn't generate a rule for that. Okay, but the question arises how we actually choose these parameters. The correct name for these is going to be hyperparameters. I'll explain the difference with just parameters when we actually have these parameters. With decision trees, with all this max depth and min samples leaf are going to be hyperparameters. And hyper here stands for the decision tree can't know which values are good or which are bad. So we tell a tree to build to be built until the depth of 3, let's say. Okay, and a tree will do it. It will grow until the depth of 3. It cannot optimize itself. It cannot actually know that it's not a good value here. Okay, so actually we as humans are setting this hyperparameter, and decision tree is going to use it just as an external condition. It's not going to learn which one is better. Okay, just for now, think of this as being set by human. Okay, of course there are some algorithm to choose it, and I will show it. But if we've got some other parameters which can be learned during the process, this will be called just parameters. Okay, we'll go into details in the next lecture, when in linear regression or logistic regression we'll have actually parameters which can be found in a nice way in an optimization procedure. But these ones are not genuinely optimized. These are given externally for now just by us. Okay, so how we define which depth is good and which is not? Again, the idea is that we've got a training set, and eventually we'll have some test set, but we need to somehow build a good model only having a training set. Okay, so we need to pretend that part of our dataset is actually a test set to check our model there. So the simplest thing to do is just to make a split. We'll take, let's say, 70% of our data to form a new training set, and 30% of data to form another one. It will pretend to be a test set. So this guy is going to be xtrain. No, I don't think there is a better name for that, not to be confused with the initial training set. And this part is going to be x holdout. For now, we don't train our tree with it. We hold it out, and we'll check our model after that. Okay, and here I depicted x and again y. Y train and y holdout. Okay, now you see the idea. We can train the model on 70% of our data, get a tree, and check whether it works with this holdout data. So we can make a prediction with our tree for this 30% of data, and then compare this y holdout with our predictions. Okay, so it's much better than just training with the whole available training set and not checking any metric like this, like accuracy. So we've split our data. It's a really nice thing to do. And typically with very large data sets, it's the only option you actually do in your practical tasks. But with smaller data sets, we can take into account that just one split is not perfect. You see, if we split our data just once, these parts are not going to be equal. Okay, so there are different instances in these parts, so definitely they are not equal, but we'd like all the feature distributions and all target distributions to be some sort of equal in both groups. So here we've got y target, and we also split it into two parts. Okay, so the most important assumption is that our test data arrive from the same distribution. And again, for now, I'm not defining it strictly, but we think that if we have feature age, it's going to be equally distributed in a training set, in a part of the training set, in a holdout set, and we hope that it's going to be equally distributed in the test set. And by that, I mean something just like histograms. So suppose The distribution in training set is something like that. But in test set, suddenly people are much younger, and it's sort of this. So it's going to be test, and this is going to be train. It's a really very bad case, so our model is not going to work like that. So with our decision tree, we are going to build splits like that, comparing age to, let's say, 17. You see, it's not going to work to generalize to test data. So this is, okay, this is bad. And good news will be if distributions coincide. Okay, this option, okay, it's test 2. Okay, this is good. Well, it's really a very complicated question. What if distribution changes with time, let's say? Actually, the simplest answer is just retrain your model. But it's a really complicated question. For now, just think of test set arriving from the same distribution. And that's why we need to do this split into training part and holdout set. We need to do it carefully, so that distributions of our features are almost the same. So in practical tasks, you just shuffle your data. If your data set is big enough, you shuffle and randomly split into 2 groups. You are going to have similar distributions because your process is random. You split it into 2 random parts. The most important part is actually to have equal distributions in our target feature. So suppose we are predicting good and bad clients, and we've got 4% of bad clients in this part, in 70% of our data, and 17% of bad clients here. No good. Yep. We've seen only 4% of bad clients in our 70% of data. Then finally, eventually in our holdout set, there are much more of them, 17%. No good. Our model is not going to work in this case. Okay. So one split is not good enough. So the most stupid mistake to do is just to have your data sorted in some way. Let's say first good clients, then bad clients, and you do a split, and it really sucks. So suppose we've got only good guys here and only bad guys here, and you split like that. Really stupid. Okay, at least you need to shuffle. So in most of applications, just shuffling your data will work. You shuffle, and then you do this split. And in sklearning, it's the same shuffle split. I think almost the same. Actually, in real applications, let's say with neural nets, when you've got hundreds of thousands instances, you just do a random split, and actually you don't have time to train a network once more. You train it with this data, and then you check it with a holdout set. Holdout. And this is training part. Okay, but if we have less data and we have enough resources, a much better estimate of our accuracy is going to be cross-validation. So now it's they go together, these concepts of overfitting and cross-validation. So overfitting is you see fitting too much, so that your model is not going to generalize. And actually cross-validation is designed to tackle overfitting. Cross-validation. So it's very similar to this train test split that we've seen, put in a holdout set, but it's a bit involved, more involved. So you just do the same split, but a couple of times. Let's say 3 times you do this split, 1, 2, 3, and you'll train your model 3 times on different parts of your data. Okay, so green will going to be a training part. So first it's these 2 parts, then another 2/3 of your data, and then another 2/3. And you'll check your metric, let's say accuracy. Accuracy is really intuitive, so just the percentage of your correct answers. And you'll check accuracy first with this holdout, 1/3 of your data, then with this one, and then with this one. So actually there will be 2 stages. Training your model, you'll get a decision tree, red one, and then you'll calculate your metric, let's say accuracy, so making a prediction and checking. So actually this will be the actual validation. So the second part, which is in red, this will be validation. How good is your model? You'll do it 3 times. You'll get 3 metrics like first we got 82% of correct answers, then 79, then 85, and as a simple metric we'll just average these. So average, and this will be, okay, let's say something like 82%. So okay, so cross-validation is actually it has lots and lots of functions, and the first one is to validate your model in a way a bit better than train test split. Okay, you see, if we did only once a train test split, only one held out set, we got 82% accuracy, let's say, but you know, maybe this part was not really representative. Maybe distribution was something different in this 1/3 of our training set. But we do it 3 times, and we get a much better estimation of our model accuracy. Okay, this setting is called, in this particular example, it's a threefold CV will stand for cross-validation. So these pieces of training set are called folds. Okay, folds are just parts, and in general it's called k-fold cross-validation, when you do k splits like that. Okay, so one cross-validation has lots of missions. One mission is to tackle overfitting, so we get much better estimation of our model performance via this procedure. But it's actually almost a silver bullet in machine learning for answers to any questions like which model is better, which setting is better. So we'll compare. So now we don't know how to set max depth, whether it's going to be 2 or 4 or even 11. We'll just do cross-validation, what I depicted here. So I'll depict it like this. We'll do threefold cross-validation. These are going to be our holdout sets. And we'll get some metric, like I will call it average cross-validation accuracy. So it's going to be average CV will stand for cross-validation accuracy. Accuracy is the simplest metric. We'll discuss much more metrics like that. Just percentage of correct answers. Okay, and we'll do the very same for each setting. For a tree of depth 2, for a tree of depth 3, and so on. And we'll just pick the best value of this hyperparameter. So cross-validation also works for hyperparameter settings. So this max depth will be tuned via cross-validation. That means we'll check different values of max depth and choose the one that works best. But cross-validation works for much more tasks. So one of them, validation. The one we already discussed is just assessing accuracy, I would say quality more generally, assessing quality reliably. So it's going to be much more reliable than just making one split. The second one is hyperparameter tuning, hyperparam tuning. And more generally, it's just an answer which model is better. So we asked which tree is better of depth 2 or 3 or 11, but a more general question to ask which model works better. So it's model selection. For now, we discussed decision trees, but we've got much more: logistic regression, k-nearest neighbors, random forest, and gradient boosting. These are all models, and we'll just pick the best one via cross-validation. So it's called model selection. Okay, feature engineering. So we can introduce more features, and again, we do cross-validation to decide whether features work or not. How do we do that? We train the same algorithm with some features and without them. And then we actually understand whether we need these features or not. So for feature engineering. Feature engineering is going to be a really exciting part of data scientists' work. Engineering, okay. So you're really creative when you engineer new features. And the next assignment on feature engineering in 2 competitions is going to be really exciting. So you'll be building different models, different features. You'll do cross-validation to actually understand whether features work or not. So then you'll iterate, you'll build some plots to get insights and to generate new features, and again check whether they work or not. So it's really a very nice application of cross-validation. Okay, I would say it's almost a silver bullet because we still don't understand it theoretically in depth. So a general setting, it's k-fold cross-validation. I would say the default is stratified. So you see we care about distribution of our features. Stratified split will make sure that you've got at least the same, almost the same distribution of your target variable. So if you have 3% of bad clients in your data set, this setting, stratified k-fold cross-validation, will take care of keeping 3% of bad clients in every split. You see? Okay, the picture for that is here. We'll take a look at decision trees. For now, yeah, here's this setting, cross-validation. I would say the default one is stratified k-fold. So you see, so these parts are validation, and we'll just keep track of our target distribution and keep it the same in any split, in any part of our training set. So this is called stratified k-fold. Okay, so if we have 3% of bad clients, we keep this 3% in each of our folds, splits. K is typically equal to 5 or 10. I would say in statistics, previously they had not such large data sets, and they stick to 10-fold stratified cross-validation. Okay, and mathematicians are snobs, so statisticians as well. So even if in your paper you don't do 10-fold stratified cross-validation, it cannot be accepted. Okay, even like that. Well, so I call it almost a silver bullet because we don't understand which k to pick. So, and the best studied case is when k is equals to the length of your data set. It's called k-fold cross-validation. So theoretically, it's the easiest part, the easiest thing to analyze. So k-fold, so it's called leave one out cross-validation. Leave one out. It's just k is equals to the length of your data set. So you first eliminate just one instance. You train your model on L-1 instances. And you do it the very same L times. Again, okay, so you train your model L times. Okay, theoretically it's very nice. So the easiest case to analyze. You train your model on almost the very same data set as you got. But you see, if we've got thousands of objects, we're not going to train our model thousands of times. So it's totally not practical. So in real tasks, typically I stick to 5-fold stratified cross-validation. Totally depends on your task. I would say in a neural net world, you just do randomized this shuffle split just once. So you only leave your holdout dataset. You don't have time to train your model even 5 times. For such tasks as ImageNet, when you've got 14 million of pictures and you need to predict 1,000 classes like dogs, penguins, cats, and then lots of species of dogs, different kinds of them. Okay, a very challenging task, and they used to train neural nets for months, 7 or 8 months. Okay, now it can be done much faster, but still you're not going to train your model several times. You just do shuffle split, and the more data you have, the more resilient is your shuffled split. Okay, for now, so this concept of cross-validation is really very important for machine learning. So it's almost a silver bullet. Whenever you ask a question, which model or which setting works better, just do cross-validation, and you don't have a better answer what is going to work best. So there is some part of data monkey job here, because we do cross-validation, we add features and see whether they work or not. It resembles data mining because we still don't understand this part theoretically, whether some features are going to work, whether some settings are going to work. So we even don't know which K to pick. No theoretical assumptions about that. So still a lot of research and some really complicated concepts like VC dimensions and like different Rademacher complexities. Okay, so really very in-depth research into this, but still we don't know theoretically which K to pick. So just pick 5. Or maybe 10 if your resources allow you. And if you have a question, I would like to add a feature. Do you think it's going to work? There is no good answer from my side. Just compare your model with these features and without them, do cross-validation and just assess the quality, whether they actually work. Okay, but it's really interesting to take a look at actual decision trees like this. So when we finally build a decision tree, an artificial example would be like that. So in this case, we have 2 features. Let's think of this as age and salary, and we split our instances into good and bad clients. Let's say yellow are good and reds are bad. We fit a decision tree. I'll show how to do it in sklearn. We restrict its depth by 3. So we set max depth is equal to 3. And it's going to build some splits. And if you think about it, these parts of the border, so an algorithm builds some decision boundary, what we call, so something to separate yellows from reds. This is going to be this boundary, 1, 2, 3. So if you think about it, decision tree checks criteria like feature as compared to some threshold, and so the borders are going to be parallel to your original axis. So let's say this split divides your data according to some criteria like feature 1 is greater or less than some threshold like 0.5. I'll illustrate this. So if you have 2 numeric features, let's say age and salary, you're going to build a decision tree for a training set that can look like that. We'll definitely do some mistakes. Okay, let's think that the best split here is this one. And you see it will be age compared to some threshold like 40 years. We'll ask a question whether age is less than 40, and we'll split our data into 2 parts, whether it's the case or not. Okay, we'll have 2 subgroups. These, the right one here in this decision tree is also a right subgroup in this picture. But you see, the part of this decision boundary is going to be parallel to salary, so perpendicular to age. And then a decision tree will further split our data set like this. So in this part, there will be salary compared to some threshold, let's say 2 to the power of 5. And the split now will be horizontal. And the same split here, again horizontal, but another threshold, let's say salary compared to 10 to the power of 4, and so on. So it's actually a restriction of the model. It can build only such decision boundaries with each element parallel to your original axis. We can think of a really unfavorable case for decision trees, and I'm illustrating it somewhere here. Okay, let me find it. You see, if your dataset is like that, if you've got a perfect diagonal split, with linear models, we'll be able to build a diagonal decision boundary very easily. But you see, a decision tree will struggle here. So it has some limitations. So actually, it works very, very well when you've got lots of decision trees, and we'll cover it in 2 weeks. But you see, a single decision tree will struggle building, this decision boundary with all these. So it looks like a ladder with all your steps parallel to original axis. So it looks like it's not doing anything smart. But at the same time, if you've got a perfect feature, like a feature that correlates with your target very well, and sometimes it's the case in practical applications. So you might want to predict the age of your client. So let's say you don't know the age, so you just don't have this feature. But you might have something really similar, really something correlating with this feature. Maybe age specified by your client in some application. You'll have lots of missing values, but still this is going to be a really good feature to predict the real age. Maybe not very clear example, but okay, you'll also have some documents. You can also have some features indicative of age. Your interests can be really very well correlating with age, so these are going to be very nice predictive features. So just in case you've got really very cool features, decision tree will be very good at determining this just at the first split. And if we think of an ideal example, whether when we add a feature that just equals to a target, a decision tree will definitely find this feature just at the first split. With the first calculation of information gain, it will find this perfect feature. It's not the case for other algorithms. So here in this article, we also compare KNN, K nearest neighbor. So I don't have time to delve into this actually simple algorithm. But with KNN, it will be vice versa. So actually, KNN will be good in this particular case, though linear models will be perfect. But KNN will really struggle to determine a perfect feature. It will mix it with all other features, and it's not going to work. So again, a very general statement that there are no perfect algorithms in machine learning. So there is a special theorem for that. They call it no free lunch. I don't know theoretical formulation, and I would say nobody actually, almost nobody ever read this theorem and went deep into details. But it says that there is no algorithm in machine learning that will work perfectly, that will work best on any possible dataset. For any algorithm, you will find a dataset that will work really badly with this algorithm. So no free lunch. Maybe it's really complicated theoretical statement, but it correlates really very well with our intuition and practical experience. So in any particular task, you start with simple algorithms, just to check whether they work. So a decision tree, KNN, and then linear models will be perfect baselines, simple models to check whether they work in your task or not. Okay, now thanks for Moore's law, we've got much more power. Okay, we can test random forest or gradient boosting, something more computationally exhaustive. And we may consider this as also simple models. Though random forest is also an ensemble of lots of trees, it's much harder to train than a single decision tree. But in some tasks, we can just think of this as a simple algorithm. Okay, let's quickly skip the rest. Okay, now finally visualizing a tree for a real task. Okay, so if we take some data set, we'll actually be building the same. I'll show you step by step. But we'll have a tree like this. You see, if we restrict it to a max depth of, let's say, 5, this tree can grow really complicated. Do I have a nicer picture for that? Okay, so we'll actually build the same tree, and we'll dig into it. We'll check what criteria are actually tested in each node, and we'll see that there is actually some set of rules generated by a tree. And in some cases, it's very interesting to show these rules to experts for them to verify whether these rules are going to work, whether they correlate with their knowledge of domain knowledge. I would say pure decision trees are used maybe now only in medicine. In medical tasks, it's really very important to understand what's going on in this algorithm. So here it's really interpretable. We can analyze it. It's not the case for more complicated algorithms. Even with random forest, when we build 500 trees and then average their results, we can't build a picture like that. So unfortunately, there is no way to build an average tree among 500. And that's why random forest will be a sort of a black box. We call it black box algorithm. It can just produce an answer, but it's really hard to understand the source of a mistake if an algorithm has made a mistake. Well, so decision trees are really very interpretable. but I would say purely they're used mostly in medicine. So there are some complications with statistical significance testing in each node. It's mostly used in medicine. But I would say in most practical tasks, pure decision trees are not used. But as a base algorithm for random forest and gradient boosting, it's used here and there. So I would say still decision trees, but inside forests and boostings are used daily and each second. So search systems are typically gradient boosting, recommender systems. Okay, so decision trees are actually everywhere, somewhere under the hood. Okay, so let's make a short break. And the second part will be programming, so I'll show the very same. Okay, and now